All right, AP Chemistry students, this is going to be our Unit 9 work for Chapter 14 on chemical equilibrium. I'm going to apologize in advance here. I have my answer key over here in a couple different pages, so I'm going to be flipping through those as we go through this. You'll hear some extra noise from time to time. All right. So here are our first our learning objectives for this unit. The bulk of this video is going to be in that learning objective 1. Because that's where a lot of the math comes from and the difficult math. So this will probably be, I don't know, maybe an hour or more, and then these will be like 5 or 10 minutes each. So they build, 1 and 2 do, and so that's one of the reasons why this learning objective can be so short. All right. So the first one, equilibrium concept. So that's just this kind of stuff here related to equilibrium, and then equilibrium expressions and how to do calculations with those. So the first question is why we need equilibrium in the first place, and that's because many natural processes as well as chemical reactions have an equilibrium to them, and so it's just important to be able to explain natural phenomena. And then in industry, a lot of industrial processes use the idea of shifting an equilibrium one way or another to get either more products or more reactants. For this one here, Kc is representative of an equilibrium constant with concentrations, and Kp is one with pressures. So if we go down to question number 8 here, we can see that we have our concentration and our pressure. So we're going to write both of these, and we have lots of practice here. I'm only going to do maybe 1 or 2 here. So we have all gases, but we can still write the equilibrium constant Kc. So we do, hold on. What color do I want? You want blue? That's red. All right, so we have Kc is equal to our products over reactants. So we have our carbon monoxide, and we have our oxygen. We raise them to the power. So there's our coefficient there. And then over carbon dioxide, that's also squared. So there you go. And we could do the exact same thing with Kp. So here's our Kp. Pressure, carbon monoxide. Pressure of oxygen. Again, we're going to square that over pressure of carbon dioxide. So that's how we write these things. It's important to note that we only put gases and aqueous into these equilibrium expressions, and we put the products over reactants and raise them to the powers of their coefficients. Now, letter B here then gives us a little bit of practice with solids. So if we have our Kc, we'd only include the gases. We have our concentration of sulfur dioxide squared. Oh yeah, so that's it there. Over our oxygen cubed. And then we do not include solids. We have a lot of practice there. I'm not going to do any more. All right, so now we have some work with this equilibrium constant expression and the equations that we can use and how to relate that to the products over reactants. So for this first one here, it says write the equation that relates those two things. It's going to be Kp is equal to, and this is when I start flipping around to make sure I get it right, Kc RT, change in number of moles. And we'll use that here in a little bit. Now for this one here, we have the equilibrium constant of this for this reaction written this way, and then we want the equilibrium constant for the reaction. It's just written in the reverse order. So if we think about the equilibrium expression in terms of that fraction of products over reactants, here's our hydrogen, there's the chlorine, here is the hydrochloric acid, or hydrogen chloride, I guess, is a gas. That's for this one. If we have the other one, that is our 4.7 times 10 to the minus 34th. So if we have all of these values, it equals this. So if all we're going to do is switch these products and reactants over so we have the reciprocal, then our answer for our other one is just going to be 1 over 4.7 times 10 minus 34th, which the value for that is going to be 2.4 times 10 to the 23rd. There you go. (16) is the first problem where I start doing some really simple math related to equilibrium expressions. See that we have 2.5 moles of hydrogen, a very small amount of the sulfur, and 8.7 moles of the hydrogen sulfide in a 12-liter flask. Calculate the equilibrium constant for this. So we can write this thing out. Our Kc is equal to our hydrogen sulfide gas over hydrogen gas, sulfur gas. It's going to be squared. And we want to solve for this thing here, the equilibrium constant. Now the problem though we have is that these brackets stand for concentration, and we're not given concentration, we're given moles. So we have to convert these moles into molarity first. And if we go through and do that, the values that we end up with are 0.725, 0.208. I usually use parentheses here when I show the work. Let's do that. And finally, that tiny, tiny number of that sulfur diatomic of 1.13 times 10 to the minus 6th. That gets us a value of 1.08 times 10 to the 7th. All right, so really simple, just plug in the values and get the equilibrium constant. A lot of these things is just that conceptual understanding of, okay, I'm given moles. What do I have to do with that before I can do calculations? Because this is in concentration. All right, 17. This is where we're going to use that Kp and Kc equation. Problem says that we have this reaction here that has a Kc of 2.24 times 10 to the 22nd. We're looking for Kp, and so there's the Kp, and Kp is equal to Kc, RT, change in number of moles, so we can just plug things in. 2.24 times 10 to the 22nd is equal to our Kc is what we're solving for, RT. So the R is going to be our 0.0821, and that's because we're dealing with pressure, liter atmospheres. And so we have temperature, which is going to be our temperature in Kelvin. So make sure that gets changed. And our change in number of moles is our 2, that's the products, 2 minus 3. So we get a -1 for a change in number of moles. So here's a -1. Now, we can, I'm sorry. Apologize for this, guys. I messed up just a little bit. We're solving for Kp. We have Kc. Don't yell at me. I'm not going to go back and start the video over. We have our equal sign here. Solving for Kp. Kc is going to be our 2.24 times 10 to the 22nd here. End up with the Kp value of 1.76 times 10 to the 20th is what I have. Boy, that seems like it might be wrong. I'm going to go through and try to remember to redo this problem, make sure that answer is correct, and then if it's wrong, I'll put it into the comments. It just seems like it should be a smaller number than that, but maybe not. All right. 18, the equilibrium constant for that was the Kc. So now we can use the same equation and just rewrite it a little bit. So we have Kc, Kp is equal to Kc, RT, change in number of moles. Now if we wanted to rewrite this, we could say Kc is equal to Kp, RT, negative change in number of moles. So we do the exact same thing. We plug in our values. The change in number of moles for this one is going to be -1 again. We have +1 here, so our Kc is equal to 3.5 times 10 to the -7th. All right. We have pressures here, and we have Kp. Notice, ladies and gentlemen, that nothing changes for how this works. You're just doing a Kp instead of Kp. So 19, we have our pressure of nitrogen oxide squared over pressure of nitrogen, pressure of oxygen. And these are always partial pressures. So we can plug those in. We have our nitrogen oxide, which is going to be 0.05. Square that, 0.15, and 0.33. And plug things in, we end up with an equilibrium constant of 0.0505. So these are just really simple plug-in numbers, get answers, move on. All right, so in this case we have just a couple other ways that we can manipulate the K values. We have two different problems that we're working on, and really all that we need to do is to manipulate the expression to correspond to the coefficients here. And we'll end up with different K values based on the number of moles that we have, because we're doing half as much nitrogen than we are here, and 3/2 as much here, and you have that there. So we'll end up with a smaller K value for these. All right, so we end up with I want to get as much room as I can here. So we would have our Kc would be equal to our ammonia, which is going to be 0.25 squared, and then we have our nitrogen, 0.11, and our hydrogen, 1.91 cubed. And we would do the exact same thing down here, only in this case, we're going to have Kc is equal to 0.25 with no exponent, 0.11 raised to the 1/2, and 1.91 raised to the 3/2. And there we go. So that is here. Oh, and we get answers too. Sorry, this is 0.29, and this one is 0.082. Okay. All right, so this is a kind of a two-step problem. We're given the equilibrium constant Kc here. We're asked to solve for Kp at the same temperature. So the first thing we have to notice with this problem, though, is that we're looking for the Kc and Kp for the reverse reaction. So this is going this direction, and then it's the same way going this direction. So the first thing we have to do for the Kc of the reverse reaction here is to do 1 over the Kc. And that gives us a value of actually never calculated that one. Just plugged it in. So we have that, and we have Kp. This is how I have it in my key, 1 over 3.8 times 10 to the minus 5th. We have RT raised to -1. So I don't know what this number is, but just go ahead and calculate that, and then that gets plugged in here to solve for Kp. And we have a -1 for the change in number of moles. #23 is actually part of Learning Objective 2. I missed this one when I was moving things around. And we know it is Learning Objective 2 because it talks about which pressures are going to decrease and which pressures are going to increase. So we're going to have to solve for the equilibrium quotient for this one and figure out which way it moves. So we're going to go past that one and come back to it. Hopefully I'll remember to do that. Oops. 28. We have our first use of an ice table here. We have moles of this NaOCl in a 1.5 liter chamber, and then we have 28% of it dissociating. So this is how we're going to set this problem up. Here is our RICE. All right, so there is our ice table. Then we can plug in the values that we have. Notice that we have moles here, and so before we can plug in moles, we have to get concentrations. And the concentration that we need, well, the only one that we have is that first moles of the reactant. So we divide through, we end up with a concentration of 1.67. On this side, we have 0 and 0 minus 2x, 2x, x, 1.67 minus 2x. There we go. And now we can just plug things in. That's not a true statement. Now we can figure out what x is. and go from there. It says that it dissociates 28%, which means that there's 72% of it left. So 72% is reactant. So we can figure out what this is going to be. And it turns out that we have 1.67 minus, or excuse me, times 0.28. That's how much it goes away. So we're left with that is equal to 0.47. So it dissociates that much. It goes away that much. And so this is actually going to equal 2x. So we end up with, I'm going to do another equilibrium list down here. 1.2 for this one. So we're going to think about, started at 1.67, it dissociated this much. We're left with 1.2. So that minus it, 78%. We could do it this way too. 1.67 times 0.72 is equal to 1.2. That is the equilibrium concentration. So there it is. We could also again get this 0.47 from subtracting that. So there we go. So the end result though is that we have to figure out how much it changed by to get this. So that's our 2x. That means that this is going to be 0.47, and this one's going to be half that, so 0.235. So we have our final concentrations. Notice that there's no like plugging this into the equilibrium expression or anything like that, because we have information about one of them at equilibrium. Once you know that, right here, once you know this, you can use that information to solve for what x is, and then plug it in to solve for the other equilibrium values. All right. Okay, so we're manipulating K again. So this is a new way. I don't think we actually talked about this in class. We have a Hess's law problem here, essentially, that this reaction and this reaction makes this reaction. We have two different equilibrium constants. Now, if these were enthalpy values, all we would do is add them, and we get our overall answer. So that's Hess's law. But because of how an equilibrium expression works, we don't use just Hess's law. Instead, we have to multiply these. So multiply those two things, and we end up with a value of 9.5 times 10 to the negative 27th. And that gets our answer. Now, incidentally, this would be the same thing. It'd be different here. So if we were to flip these around, we had the hydrogen sulfide, or the hydrosulfuric acid on the product side, and the hydrogen and the this thing here on the reactant side, we would switch the signs, right? So flip, switch the signs of enthalpy. But for an equilibrium expression, the equilibrium constant, because of how expressions are written, we would do the inverse instead. Also, as we're going through these, if we say put coefficients in front of all of them for whatever reason we had to, here we just, enthalpy, we multiply by 2. For equilibrium constants, we square. So that's how we treat equilibrium constants differently in problems like this for than enthalpy problems. All right. 30 is going to be the exact same style problem. I'll get the answer up here for you, but I'm not going to go through and do the work. It is 3.97 times 10 to the minus 6th. So there's that answer. All right, 43. Let me find that one. All right, so this is the first one we're going to be asked to solve for the calculations at concentration. So, in terms of these chapters that we work through, ladies and gentlemen, at the end of the year, this style of a problem is the first kind that I would say is difficult to understand. But once you have a concept of those ice tables and how those work, it starts to progress pretty easily. Understanding of what you solve for and what you plug in and how that all works becomes very, very useful. All right, so let's do our ice table. Here is our H2 plus Br. I have our initial concentrations here. Notice again that they are given to us in moles. So this is an interesting one. I forgot about this problem. So we have 0 of the reactants. That's kind of silly. Like, well, we have reactants, but there's nothing of them. This is really a good example to show that we don't really have reactants and products in equilibrium. We have left and right side. We still call them reactants on the left-hand side just because that's what we know them as. But we also want to make sure that we understand that that designation doesn't really apply to equilibriums. So we have our concentration of this. If we calculate it out, it's going to be 0.267. Now, in class, we said that we would always put negative x on the reactant side, positive x on the product side. In this case, that doesn't make sense. We can't subtract something from 0. Can't have negative concentrations. I will tell you, if you do it this way, you will get the right answer, as long as you keep track of the signs. But conceptually, it makes a whole lot more sense to do it this way. So and then we have x here, we have x here, 0.267 minus 2x. We can put it into equilibrium expression. 0.267 minus 2x squared, because of the coefficient here, over. I'm going to skip ahead and maybe see if you can see how that works. So if we have x on the bottom, and x on the bottom, x and x, x and x, we end up with x squared. All right, and now we can plug things, or now we can solve for the x. Oh, here's the Kc over here. It is at number 2.18 times 10 to the 6th. Now, this is kind of a nice algebraic thing, so we can get away from the quadratic in this problem. Since we have this whole value squared on the top and this whole value squared on the bottom, we can take the square root of both sides. And that gets rid of those squares. And that's kind of handy when doing these kind of problems, because with the squared x in there, you're going to be doing a quadratic, and without it, you don't need to. So we have our 0.267 minus 2x over x equals, the square root of that guy is 1.48 times 10 to the 3rd. Go through all this algebra, we get an x value of 1.8 times 10 to the minus 4th. So our values here for the hydrogen concentration, 1.8 times 10 to the minus 4th, and that's molar. That's always molarity. So that goes for that one. It also goes for that one. And then this one's going to be 0.267 minus double that. So we put this down here. HBr is equal to 0.267 minus 2. There's my 2x, 2x, 2x. So the 2 here. Concentration for that guy comes out to be 0. Oh yeah, pretty much the exact same thing. Look at that, 0.267. Well, Once you know it, we have a huge K value, which means that this equilibrium is going to lie to the product side, so much so that we have almost nothing on the reactants. Very small amount gets shifted, so much so that we still say that we have the exact same amount of products. All right. 48. This one is the same kind of a problem where we have moles given, volume of a flask. In this case, we're going to have moles of reactants, none of the products. So we would have our rice table. Oh, it didn't change. I guess we'll do this one in red. We have our plus carbon dioxide, water vapor. Now, we still have to leave the water in there because it's gaseous. If this was a liquid water, we would take it out. So now we have concentrations 0.8, 0.8. We have 0, 0. After I even said that this is not given to us in concentrations, I go and do that. So now we have 0.16 and 0.16 minus x plus x plus x minus x minus x x x. So we end up with our K value, which is going to be 4.2 equals x squared over, now again it's going to be this whole expression times this whole expression. I'll write it out here. 0.16 minus x, that is a 6 if you believe it. 0.16 minus x. Now another way to write this would be 0.16 minus x squared. And then if we have a squared expression on the top, a squared expression on the bottom, we can go ahead and do that square root again. Isn't that handy? So we end up with a value of x is equal to 0.11. And then we can go through and do all the work. Should do this. 0.16 0.16 minus x. We have our values. All right. All right. Let's see here. 49. Let's see. I'm not going to do this one here. I'm going to move on. Oh, good. We get to learn objective 2. Oof. All right. I was learning objective 1. I wonder how long that took. I have a different answer key for this. All right, I'm back. So we have the reaction quotient. Now the reaction quotient is symbolized as a letter Q, and it's QC. And this gets compared to the equilibrium constant, and so that's how it's different. Is that one is at equilibrium, and one is being used to determine if it's at equilibrium. So we don't know. We're given values, but we don't know if it's at equilibrium or not. So that's how we can use Q. We compare it to K. If Q and K are equal to, then it is at equilibrium. And if Q is larger, one thing's happened. If K is larger, it's the other thing. We'll look at those when we get to the problems here in just a second. All right. 3 problems that we go through. Now, I want to do these problems. We talked about these guys when we did them in class, that I always write out a rice table anyway. just because this helps organize all the information. We're given concentrations now, which is kind of nice. We don't have to worry about converting them into molarity. Let's see. Let's look at these guys here. 0 and 0 and 0. Hopefully those don't throw you up. Remember, if it has sub-zero, it just means it's initial, starting initial. So we have our concentrations. N2 is going to be 0.6, H2 is going to be 1.2, and ammonia is going to be 0.48. Minus x plus 2x and then we could put it into an equilibrium equation, solve for x's, get concentrations and everything like that, but we don't need to do that. Instead, we can figure out which direction the equilibrium is going to shift just by solving for Q. So here is my Q. It's the same thing. It's products over reactants. So here is our concentration of ammonia. Hydrogen, and we can solve. Q is equal to 0.48 0.48 0.6 1.2 squared, and that Q gets us a value of oh darn. I don't have this one. I think it's 0.87. That could be wrong. I don't have a calculator near me right here, so if that's a little bit off, use your answer. I do know that this answer is smaller than 1.2, and since it's smaller than 1.2, that means that we have, in terms of our fraction, not as much of the products as we need. So it's smaller than this, which means to get to this, we have to increase this top number. That top number has to go up, which means that this is going to shift from reactants to products to reach equilibrium. All right. #41, this is the one that I have the key for here. It's exactly the same. We have exactly the same process, just have this different reaction here. So I'll go ahead and do this. We have our ice table again, 2 NOCl. We can plug things in. Again, we're given concentrations, not moles, which is kind of nice. Saves us a step. 0.5. Chlorine is 0.05. Minus 2x, 2x, 2x. Have my ice table. Oh, but look, it just says determine which way it'll shift. So that work is unnecessary. So now all I have to do is solve for the Q. And we have our initial concentrations again is what we plug in here. 0.05 squared. Those two, hold on. Cubed, because this is 0.05 squared, and this is 0.05. Multiply those together, they'll get 0.05 cubed, divided by 0.1 squared, and the Q we get for this one is going to be 0.0125. Again, it is smaller than the K value, which means that in order to get closer to this number, our top number is going to have to get larger. The top number has to get larger. It's going to be shifting towards the products. 42 is another problem here that's kind of the same concept, only at the end. If we look at this last line, it says, what will the final concentrations be at equilibrium? So this is why I like to do ice tables every single time, because sometimes I don't read the entire problem before I start the work. And in this case, because of that last line, I'm going to need my my ice table. So we have our concentrations, 0.05 of those two things, of the hydrogen gas and iodine, and 0.1. Those are the same concentrations as before. Look at that. All right. Minus x plus 2x, 0.05 minus x, 0.05 minus x, 2x, oops, 0.1 plus 2x. Have Kc is equal to we have our concentration of hydrogen iodide squared on the top, and then we have our hydrogen, we have our iodine, and we can plug our values in. We have 450 for the equilibrium constant. It's equal to 0.1 plus 2x, that's squared, over squared as well. Now, when I did this work, yeah, I did that. You can go ahead and do that same thing we did before, so you can get away from doing the quadratic in this problem again. Take the square root there, it gives you the squared expression on the top, squared expression on the bottom. We end up with a value here, let's leave it in red, of 21.2 is equal to 0.1 plus 2x over 0.05 minus x. So now we can solve for x. X comes out to be 0.041. And now I can plug things in to solve for my final concentrations. Now, I did skip over this at the beginning because the very first problem of this, the first part of the problem it says is this system at equilibrium? To solve for that, we should have gone through and solved for Q and see, does it equal to K? And then we would be able to say yes or no to that question. Now, and then which way would it shift, either left or right? Now, because of this last line here, what will the final concentrations of the equilibrium be? You can kind of just skip ahead to solving for that because it tells you which way it'll shift. We have a value of 0.041. Since we're subtracting it here, this number is going to get smaller, that number is going to get smaller, this number is going to get bigger, so it's going to shift from left to right. Now, if this was a negative value, which it could have been depending on the concentrations, it would have been shifting the other direction because we'd be subtracting a negative, and that would be an addition. So, although this is an important step and maybe one that we should have done to show which way it was going to shift or which way we were predicted to shift, this work tells us that same thing. So I just went ahead and went with that. The final concentrations, by the way, are going to be 0.009 for those two guys, the hydrogen and the iodine. And then the concentration for the other one is going to be 0.182. Or I guess, no, 2, yeah, 0.182. So this is the hydrogen iodide. All right, so there's learning objective 2. Now we have learning objective 3, which is Le Chatelier's principle. All right, now I got to go back to my other answer key. Flip, flip, flip. So when we talk about equilibrium stuff, we're always looking at, so far, whether it is at equilibrium, how it will shift to reach equilibrium given concentration values, and other kinds of calculations related to manipulating K and whatever. Now, Le Chatelier is really where the equilibrium concept becomes applicable at the industry level. So let's say we have an equilibrium reaction like this, H2 plus N2 makes NH3. We have a K value for this of 1.2 at a specific temperature. I don't know what temperature that is. We can see that this reaction, let's get this balanced, 2 and 3, is going to favor the products, but just barely, because that value is very small. If it's 1, we say it's, depending on the coefficients, you have equal amounts of both reactants and products. So just being above 1 means that it shifted towards the products just a little bit. Now, this is a really important reaction. Ammonia is something that we need, and so a lot of work was done into what could be done to shift the equilibrium towards the product side. And incidentally, one of the things that could be done is to heat this up. So heat it up to about 900 degrees Celsius, and that shifts this. So if we have a K value at 900 degrees Celsius, I don't know, it's something like 52. I'm making that number up, but it's larger than it is here, so we're able to shift it towards the product side. So this is really the importance of Le Chatelier's principle of being able to move the equilibrium one direction or the other. Hold on. Should have this in there like that. Now, there are lots of different ways that we could shift that equilibrium. One is by increasing the temperature, like I just said. We could also increase or decrease volumes. We could increase concentrations of reactants or products. So all of those things can be done to shift that equilibrium. And what we're doing with Le Chatelier's principle is determining which way the equilibrium will shift based on that additional stress, whether increasing the temperature or decreasing the volume or something like that. And so I'm going to use this phase change of water to explain that a little bit more. Let's say that we have a container like this, and then inside this container we have a beaker, and that beaker is full of water. So here is it is on a bench or something like that. So here's that container on a bench, and it has water. So over time, this is going to evaporate. So we have a little H2O molecules all in here. So it's evaporating, 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 and then we get these little droplets along the walls. So it starts to condense. So we have this vessel that is now in an equilibrium. The water is evaporating, and then it's condensing on the walls. It's evaporating, it's condensing in the beaker. It's evaporating, it's condensing on the surface of the counter. Now, let's say that this container is flexible. So now we have a container that is much, much larger. And there's our beaker. It's filled with water. Now we have all of these molecules here, these water, and we have some molecules of water around there and there. But since we increase the volume, there is more space for the water to evaporate. And so more of the water is going to evaporate. Right? More is going to evaporate, more is going to evaporate until it starts condensing again, condensing, condensing, condensing on the table, and reaches a new equilibrium. So in this case, if we change the volume, we decrease the volume, we end up providing more space for the gas to exist, and so the water is going to go into the gaseous phase more readily. So this is one way that we can change what is going on in the equilibrium system, or change the process, and then we can see how it impacts it. So there's other ways that we're going to see down here, but this is the example of how an equilibrium can be shifted. All right. So in this case, let's see. Let me read this real fast again. We have sulfur dioxide, chlorine, and this SO2, the sulfuryl dichloride compound, and we're going to add things to it. Now, the easiest way for me to think about this is to add something to one of the sides, and if we add to that side, it's going to shift towards the other direction. It has to shift to the direction to reach equilibrium. And that works for concentrations and temperature as well. Now for pressures, we're going to look at that here in just a little bit. But in this case, we're adding chlorine gas to this, so it's going to shift to the right. We have extra of this, so it has to shift towards the sulfuryl dichloride. Now if we're going to remove the sulfuryl dichloride, so we have less of this, that is leaving an opening for more of this to be produced, so it's going to go towards the right again. If we're going to remove some of this, removing some of the reactant, so it's going to go this direction. And the temperature remains constant, that's just information. All right. 54. Another one dealing with concentrations. We're removing things. So in this case, we have some of the carbon dioxide is removed. If the carbon dioxide is removed, it's going to go towards that void that has been created. Some solid sodium carbonate was added, so now we have more of the reactant, so it's going to go to the right again. Some solid sodium bicarbonate was removed, and it goes back towards that, so we have that. So we have, let's see, 54. Oh yeah, this one here. I wanted to double check my key to see if I was right. So these are wrong. This is a really common mistake, and I just made it. If you remember here, when we do our equilibrium expressions, we would have our, all we would have is H2O. We have H2O here because it's a gas, not a liquid. We have our CO2. We don't include the solids, and the solids are not included in the equilibrium expression because they're not going to impact the equilibrium. They're not going to impact it because they don't change the volume of the system. And the concentrations don't change of a solid either. The concentrations of an aqueous changes. So the two things we need to keep track of in an equilibrium system is whether or not the volume or pressure would change because it's a gas, or the concentration would change because it's aqueous. Since these guys are not either of them, they have come on. Oh, this just stopped working. There we go. No effect. Oh my goodness. I apologize, guys. Let me try this. Whatever. Erase. No effect. Same thing here. So if you have a solid changing things, we do not change the equilibrium. It doesn't shift it. All right. 55. This is where temperature comes into play. Another one with temperature that might be easier to look at. 58. Okay, we'll just go with that one. Now, the changing of temperature is based on enthalpy, and this is the most difficult one for me to remember, and this is how I deal with it. So another way to talk about an enthalpy value is to call it heat. Let's use red for heat. This is heat. This is heat. Since it's a negative, it's released. Since it's a positive, required. It's required. Now, if we think about it just in terms of heat, we don't have to worry about the numbers. All we do is say that since heat is required, it becomes a reactant. Oh, let's leave it that way. Heat plus A owes A B. Now we can look at it in terms of a reactant or a product. If we're going to increase the temperature, we just look at which side the heat is on. We're adding more heat, just like if we're adding more reactant A. If we add more reactant A, it shifts towards the right. Add more heat, that's a reactant, shift towards the right. So this is shifting towards the right. If it's a negative, the heat's going to go on the other side, so we'd have AB plus our heat. And again, we can think about it. We're increasing the heat. We're adding energy. Heat is going to then be added to the product side, and it goes this direction. Just like if we add some of this, add concentration of AB, and shift towards the left. All right. And the last one's going to be no effect, because there is no enthalpy value there for that one. All right. Pressure. So we've looked at concentration, we looked at temperature, and enthalpy. Now we look at pressure. Now if we go back to that example with the gases at the beginning, as we increase the pressure, increase the volume, we decrease the pressure. So decrease in pressure shifted towards, let's do it this way. We had water as a liquid. We had that equilibrium with water as a gas. As we decreased the pressure, it went towards the side with the gas. Or another way to say this, it goes towards the side with more gas molecules. So we'll see an example of that, I think, the very last one. But otherwise, if we just have solids and liquids, we go towards the side with the gas. Now, if we were to do it the opposite direction, where increase pressure, it's going to go away from that side. It's going to go towards the liquid or solid. So let's go through these to see if we can apply that. A, no effect, because they're both solids. There is no gas. B, no effect, same reason, no gases. In this case, it's almost exactly the same as this, only we have a solid instead of a liquid. It's going to shift towards the side with the gas. We are decreasing the pressure, right? Oh, darn it. No, we're increasing the pressure. I have to go back and change that one. Increasing the pressure goes the opposite direction, towards the side with this less gas. So less gas, increase the pressure. This one here, we have no effect again because we have the same amount of gas molecules on both sides. On this one here, it's going to go towards the left. Again, an increase of pressure will go to the side with less gas molecules, decrease, more gas molecules. So less decrease of pressure, more gas molecules, increase of pressure, less gas molecules. Less gas molecules because the coefficient there is 1 mole to 2 mole. All right. Okay, now we have another piston. I remember pistons are just like syringes. Think about it as a syringe. And this is a mixture of all of the different concepts we've looked at. So an increase in total pressure is going to go towards the side with fewer gas molecules again. So we're going to go towards the iodine, adding aqueous iodine, the dietop. It's going to go this direction. decreasing the temperature at a constant volume. Well, I'm missing some information here. I cannot, oh, yeah, I can't answer that question. We're missing an enthalpy value on this. 57. Huh. There should be an enthalpy value here. Since there's no enthalpy value, we can't answer that. I'm not sure what happened to that. This one has an enthalpy value. All right. 58 and 59 are the same idea, so I'll talk through this one and then give the answers for the last one. Temperature is raised. Since it's a positive, we put heat over on this side. So if we add temperature, we're going to go towards the other side. We're increasing the reactant because heat is a reactant. More chlorine gas is added. There's the chlorine gas. It goes to the other side. Some of the PCl3 is removed. This direction. Pressure on the gas is increased. All right, so we have 2 gas molecules on the product side, 1 on the reactant side. So it's going to go to this side. Fewer gas molecules. Catalyst. No effect. I think I missed that problem before, but if we add a catalyst, it doesn't change the equilibrium at all. All it does is allows it to reach equilibrium faster. Finally, the answers here for 59. I'm going to go like this. This way, this way, this way. No effect. No effect. Let's talk about this last one. We're adding helium, so the pressure is going to go up, but when we talk about pressures, it's only the pressures of the things involved in the reaction. And since the helium is an inert gas, it's non-reactive, it's not going to react with any of these things, these species here. It's not going to shift equilibrium one way or the other. So it's just the partial pressures of these guys. All right, ladies and gentlemen, that should be it. Thank you very much